Good afternoon, everyone. Today we have the great pleasure to welcome Professor Leandro Barbosa. Professor Barbosa works as Associate Professor at Universidade de São Paulo, USP. He's primarily interested on small-angle X-ray scattering and on transmission electron microscopy. In the last years, he has been dedicating himself to the study of nanoparticles with cubic structure, cubosomes, for the creation of drug delivery systems. He is also interested in determining the envelope of proteins without resolved structure and in determining the structure of protein complexes. He also studies the effect of denaturant agents on the structure of proteins. He has 66 research papers published that have been cited more than 1,000 times together. In addition, he co-authored 5 book chapters. Welcome, Professor Barbosa. Thank you so much for being here. Please feel free to start your talk now.
Thank you very much for this very nice presentation. I will start to share my screen right now. Can you see my screen?
Yes.
Yeah.
Leandro, can you speak louder?
Yeah,
Okay.
sure.
Nice.
Okay. So first of all, thank you guys to attend this meeting today. And before that, I would like to thank the organizer for this invitation. I was very, very proud to be selected to be one of the speakers of your webinar. So thank you very much. So today we are talking a little bit about the use of scattering techniques. As in particular, today I will talk about those about 2 techniques that we used a lot in our lab, and to talk a little bit to you about our lab, we inside our group we have more or less 2 different kind of research fields. The first one in this line here above regards the characterization of nanostructures like liposomes and cubosomes, and I will talk about those kind of structures today. And the second line that we have a lot of contribution as well is the use of small angle X-ray scattering technique to study proteins in solution. So, in this particular case, our main interest is try to get more information on the protein structure in the absence and in the presence of different kind of small molecules like nucleotides or denaturant agents or something like this. So these are the 2 main research lines that we have in our group nowadays. To talk a little bit to you about the nanostructures, I'm a physicist, as he already mentioned in the beginning of his presentation. Physicists start to think a little bit more carefully in the nano world from our point of view. And more or less in 1959, with Professor Richard Feynman, a very, very well-known physicist, American physicist, and he in the APS, which is the biggest meeting from the physicists in the world, the American Physical Society meeting, he make a speech and mention what should be the impossibility, or if there were some impossibility to write all the acknowledgement that they have in, let's say, an encyclopedia, all those pages inside a pinhead. And it was very nice because he made some very simple calculations and he showed that it's possible to write everything there. Of course, you just need to control the size of the letter. I mean, the letter should be nanometric, and you would be able to try to do this. And after that, physicists start to take a better look, or to take a more careful look in this particular feature of the matter. This slide here is just to have more or less an idea of the sizes that we are talking about. When you get a red blood cell, which is more common for us to understand, it has more or less 70 micrometers in diameter. This can 7 to 8 nanometers. And here is, for example, the well-known coronavirus. He has around 100 nanometers in diameter, much smaller than the regular cell. And it's very important for us, for physicists, and for people who work in the nanometer area, let's say, or the structure area to have this kind of sizes in mind, because it's important to have an idea of the size of the structure that you are trying to study to get more information, to then be more precise and choose the most suitable technique to use to characterize your system. So for example, today we are talking about the structure that are more or less in this range of sizes from 10 to a couple of hundred of nanometers. And in this case here, we are talking about, for example, liposomes, which are very, very well-known structures from self-assembled structures that we use, for example, for drug delivery purposes. But we can also have polymeric nanoparticles, micelles, and so on, that have also some industrial use. For example, in the industry of soap and the derivatives of soap, it's very important to characterize the size of your structures are more or less around these sizes. Here is just to compare and how big and small is the nano world. On the left side, we have the well-known coronavirus. It has more or less, this is wrong, I'm sorry. This is not 100 micrometers, this is 100 nanometers long, I'm sorry. And here on the right side, we have a cell infected by this virus. So each yellow dot that you can see here, for example, this one or this one, each one of them is a virus that are trying to enter, to getting out of the cell. And the cell is completely lost, I mean, it's completely damaged. And these tentacles here, they are not so common in this kind of, this particular case, but they appear due to the interaction of the virus with the cell membrane. And why it's important to know more or less the size that I mentioned to you. This is important because knowing the size that you have, knowing the size of your, or at least the order of magnitude of your scattering particle, you can better choose the experimental technique that can be more useful for you, depending on what kind of information you'd like to have. For example, if you are using, if you want to study virus or some kind of DNA assemble or system similar to those, it's better to use, for example, crystallography for small structures. Sorry? Sorry, I didn't understand the question, sorry. No? Okay. Okay, no,
I think it was just noise.
Okay, sorry. So you can use crystallography when you need to get, for example, information on the atomic position in some particular structure. Of course, nowadays we can also have a cryogenic electron microscopy, which is also a very, very important tool to give information on the atomic position of atoms, on the atomic position inside a protein. So then you can characterize your protein. And you can also have here a small angle X-ray scattering and small angle neutron scattering, which are both very, very similar techniques. Of course, the first one deals with the interaction of X-rays with matter, and the second one deals with the interaction of thermal neutrons in the neutrons with the matter. So they are slightly different from the physical point of view, from the interaction of the X-ray and neutron with matter itself. But from the practical point of view, they are quite similar, and they can give also similar results or even complementary results depending on what you are looking for. So the outline of this presentation today, I will mainly focus in two experimental techniques: small angle X-ray scattering and dynamic light scattering. And then we go to, we'll show you a couple of examples on how to use both techniques to try to characterize your system. This is a bench machine from small angle X-ray scattering. All the small angle X-ray scattering machines, they are quite similar one to each other. The main issue from every small angle X-ray experiment is that you have a source, an X-ray source. Here in this case, we have a conventional X-ray tube. Then after that, you have a monochromator, because when you produce the X-ray, you produce you every time you produce window of wavelength, and it's important for us to get a very, very narrow window of this wavelength, of this energy, this X-ray energy, so we can select then the appropriate energy or wavelength here with the monochromator. After the monochromator, the evanescent X-ray beam passes through what we call a collimation system. This is only to get out the parasitic beam of the main beam, and then we have like a dot propagating in the after the collimation system and hit here the sample. Of course, today I will talk about those nanostructures, generally for biological, biochemical purposes, nanomedicine and this kind of structures. The X-ray interacts with the matter with your sample, with your nanoparticle, and then some of this X-ray, after interacting with your sample, will hit the detector at the end of this small tube here. Here is something around the order of magnitude of 1 meter, more or less. This can vary a lot. We can have even 10, 20 meters, 30 meters far away from the sample. This is what we call sample to detector distance. So in other words, to make an schematization, here is the same thing, but in a schematic view, we have the X-ray source that can be a conventional X-ray tube, as I just showed to you, or even a synchrotron. Polymetric X-ray from this source. Then we have a monochromator, collimation system, sample holder. Because of the physical interaction of the X-rays with biological matter, most of the X-rays will not interact with with your sample, and they will cross your sample without interacting, and will hit the detector here in a position that what we call the zero beam position or the directed beam. And some of them will interact and will scatter to a certain position here in the detector. This is the reason, because this technique is named small angle X-ray scatters, because of this guy here. Since we have a quite large distance from the sample to the detector, this guy will be small. This is the reason that we have the small angle X-ray scatter. We are seeing the scattering of X-rays at a kind of long distance from the source, from the sample, and this is the reason that we have a small angle in the name of the technique. After that, when you take a look in the detector, of course, this depends a lot of what kind of sample do you have here. I got some standard sample where you have very, very well defined scattering positions. This is because we have a very, very organized system. And we measure the distance from any scattered X-ray as compared to our zero position using the well-known scattering vector Q. The scattering vector Q is vectorly defined as the difference from the outcome scattered X-ray with the outcome non-scattered X-ray with the directed beam. And its units are in the reciprocal space, so we are talking about meter to -1. Of course, in our case, we are using nanometers to -1 or angstrom to -1 because of the wavelength of the X-ray. It's important to mention that generally, the wavelength of X-ray is something around 1 up to 2 and something angstroms. So the 0.1 or 0.2 nanometers to nanometers. When you get the azimuthally integration of this image here, and then you can get something like this. This is kind of an histogram or something related to how many X-ray photons reach each position of the detector as I'm going apart of the zero position. And in some specific position, for example, like in this position here, we may have a peak, and in the second position here, you have a second peak. The third and fourth peak is not, we cannot see here with the naked eye, but they are there when you integrate. And in particular for symmetric structures like crystal structure, we have the position of these peaks reflects the organization of this structure as a whole. Of course, one of the main issues of the technique regards the X-ray source. You may have a conventional X-ray tube, as I already mentioned to you, but you may have also a synchrotron light source. So this is our Brazilian synchrotron light source. It's not operating nowadays. It's closed. It closed, I think, last year or 18 months ago, something like this. And it's closed because we are building a new one. This is serious. I think most of you have already heard about it, mainly in the press or something like this. And we have a very, very huge structure, a very, very powerful machine. And in this machine, we have the acceleration of electrons and the deflection in some specific position. And those deflections of those electrons in these specific positions give rise to the appearance of X-rays. And these X-rays will be used as the source to the Sachs beam line. So we have all of this machine here, only to have a special and a particular kind of source to the X-ray to be able to make some particular experiments. So talking about dynamic light scattering, the technique, it's sometimes we call it as a simpler technique as compared to small angle scattering, but we must pay attention with dynamic light scattering because it's a kind of very, very tricky technique. Because when we measure dynamic, when we make this kind of measure, we are looking for information regarding the size of our nanostructure. But we must take care because the technique does not measure the size of any particular particle in solution. It measures what we call the coefficient, the diffusion coefficient or the translational diffusion coefficient of the particle, and then the software of the most of those DLS equipment they have with some software for analysis that comes with the equipment itself, and you must take care when you use those softwares and also when you get that information, because there are some assumptions that are made in order to use this technique. So the dynamic light scattering, to talk about dynamic light scattering, first of all, we need to talk about the Brownian motion of the particles, or in our particular case, the nanoparticles. The Brownian motion was first observed by Robert Brown. He was a British botanic. He was studying pollen from flowers, and he realized that when he used the microscope, we must realize that the microscope was invented less than 100 years before him. And he was taking a look in the microscope, and he realized that the pollen kind of have some kind of movement inside the water. And he believed that those movements arise from the fact that the pollen was a living structure. And he wrote the paper regarding that the pollen is a living structure. He's proven that the pollen was a living structure because he was moving around in water. To be sure to check his result, he used some powder of oak as well to compare, because he knows that oak, when you burn wood, you have oak, and the oak is not able to, of course, he knows it was not a living structure. And when he put the oak in water, the powder, he realized that he have the same kind of movement. And so he could not conclude any longer that the pollen was a living structure because it was moving around, because the oak powder was also moving around as well. And he could not explain this kind of these observations. He observed that, but he was not able to explain. Only almost 100 years after him, in 1905, Albert Einstein made his PhD thesis on the Brownian motion, and the statistical mechanism of the Brownian motion, and he realized that indeed what was going on there in the Brownian motion is that in a specific period of time, very small period of time, the number of hits from small particles in one side of the pollen or of the oak was different from the other side of the pollen. So this gives rise to a small resultant force in some particular region, in a particular direction. A moment later, the number of hits, the number of hits in one part is different from the other parts, then gives rise to some particular force to other direction. Then you have this kind of movement, this kind of random movement depending on the number of hits that you have in one part and the other part of your particle. And he made his PhD thesis on the statistical mechanics of this kind of movement. So, and this is the most important thing from the DLS. The DLS, when you develop the theory, the physical theory of DLS, the first thing that you may write is that I'm supposing that the particle is under only the action of the Brownian motion. There are no other kind of force acting on my nanostructure, my nanoparticle, only the Brownian motion. Yeah, so you cannot have any kind of interaction between two near scattering particles, two near nanostructure particles. The technique itself, it's kind of simple. You have a laser beam here. Generally, the most equipment uses the red wavelength, which is something around 633 nanometers, or the green one, some of them use also, it's 533 nanometers. So you have your laser here. Here you have your sample holder. And there are the scattering, the interaction of the scattering particles in this particular center here. And then the light scatters through the correlator. And the correlator makes this kind of measurement and after that goes to the computer, and then you may create your self-correlation function. Taking a look that inside our sample holder, we have here the laser, then we have the interaction, and of course it's interaction all along this path, but it's only important for us what is going on here in this region here. So what the correlator measure is something related to the number of scattering particles at any specific time window here in this small volume of illumination. Then he gets this kind of information, this kind of intensity fluctuation, and he makes a scattering curve, intensity variation along time. And this curve here gives rise to what we call the self-correlation function, with the G2 of T. This function here, which is something similar to this one. This is nice because when you have this kind of self-correlation function, we must realize that since what we are measuring, the intensity that we are measuring is proportional to the number of scattering particles inside this illuminated volume, if I have a kind of constant number of scattering particles there, it means that it's kind of difficult, or better saying, takes a longer time to this scattering particle to get away from this illuminated value and change this average and change the number of scattering particles there, as compared to a small particle that we can have several of them going in and going out this illuminated volume. This means that the correlation for small particles, it's lost much faster than the correlation from larger particles. And just taking a look at this kind of information, you can, of course, should be a comparative result. You can say, oh, my scattering particles become smaller or bigger as you take a look at the self-correlation function. But you have to bear in mind that all of this information is only valid if you have only and just only the Brownian motion taking place in your experiment. And this is what people do, or actually this is what most of these equipments perform to you. You get the self-correlation function, and then you make some assumptions that you have just this diffusional movement taking place. If you have this kind of behavior, it's possible to make a kind of to make a fitting of the self-correlation function, and then you get the information of your translational diffusion coefficient. This is the final measurement that you have. Then most of the machines, for some practical reasons, they make an assumption, okay, this diffusion coefficient, it's the same diffusion coefficient as a solid sphere with some particular radius, or in this case diameter, had in solution. This is the well-known Stokes-Eisen relationship between the translational diffusion coefficient and the hydrodynamic diameter, and this is valid only for spheres in solution. Of course, several papers in the literature, they report this kind of information, but you should bear in mind that this is true only if you have the Brownian motion taking place in your system. And with this information, you can calculate some kind of interesting behavior. For example, here, I showed you an example that you have a long time, the aggregation of some particular sample, because here you have this kind of diameter, and you see that a long time, the diameter is increasing. So you can have general information of your sample. This is nice. This technique is nice because it's a very, very nice technique to check the size of your sample and to check if you have some kind of aggregation in the process of producing your nanoparticles. And this is nice to also to check if you have a clean sample, because the presence of dust can interfere a lot in this kind of experiment. So it's a very, very nice technique. And also another important thing regarding DLS is that the amount of sample needed to make an experiment is extremely low. So you can have very nice results with very, very small amount of sample. So now I'm staying more or less half of the talk talking about the techniques. Let's stay another half of the talk showing to you some examples. Now, this is our, of course, I'm a guy from the experimental techniques itself, but I also have some research lines that I like very much, where I applied those techniques that I just showed to you. And one of them is the drug reproposing methodology. This is a very nice methodology. I started to work with that around 5 years ago, more or less. And the main idea here is to use some well-known drug to treat some kind of disease that this drug was not performant to be used to. Here I show to you some of our contributions regarding this kind of area. And this particular one regards proteins, I will not talking about that. But this one here, it's very, very nice. I will say something about it in a while. So this is the case of bupropion. This line of research that we have in our lab, it is performed in collaboration with Professor André Temponi from the Instituto Adolfo Lutz. It's a very, very well-known institute here in São Paulo and also in Brazil that work with parasitary diseases like leishmaniasis and malaria, these kinds of diseases that, unfortunately, Chagas disease, this kind of diseases from underdeveloped countries like Brazil. And he had some kind of information that the bupropion, when entrapped into liposomes, was able to kill more leishmaniasis parasites as compared to the drug in the absence of the liposome. And so we would like to study how was the drug located or where was the drug located inside the liposome? This was our main question in this study. This is the scattering curves of the liposomes in absence in the presence of the drug. In the absence, we have the open circles, in the presence, in the open squares. And they are very, very similar. However, we can see some small difference around here from these structures. And we try to use that small difference to try to infer something about the drug. What we know is that buparvacone increased the zeta potential of the nanoparticle. If you don't remember, the zeta potential is the measurement of the electric potential in the shear plane of your nanostructure. It's a very, very well-known technique to, and then you can have an idea of the total charge of your nanoparticle. And here is the DLS, the hydrodynamic diameter obtained with DLS. And we see that in the presence of buparvacone, we have an increase in the zeta potential. This indicates for us that buparvacone must reside somewhere near the polar head of these liposomes. And here we have a decrease in the hydrodynamic diameter, indicating that its location should also change the packing of the hydrophobic part of the liposomes. So we went to analyze this. I did not put so much details on the mathematical modeling for the site, but we can talk about that later if you'd like to. There is no problem. But mainly we here have a liposome, so we have a very, very unilamellar liposome. We have here three main regions: the polar head of the liposome, the CH2 part of the liposome, and the CH3 part of the liposome. And this is like a mirror to the other side. So this is the, let's say, this is the upper left of the bilayer, and this is the inside leaflet of the bilayer. And then you have water on this side and water on this side, and this is a sphere in solution. When we make we make this kind of information because we would like to model how is the electron density profile changing along this direction here in our system. Here we have, so the electron density profile. 0 is the middle of the bilayer, exactly this point here. This is 0. So this is a symmetric bilayer. So what you have in the right side is what we have in the left side. This is the organization of the lipids, only you to understand. So we with those results, with those models that we present, you may note that we have a kind of a bump here and here. The solid line represents the electron density profile of the system in the presence of the drug, and the dashed lines the electron density profile in the absence of the drug. And with this increase in the electron density profile in these two regions here, actually this is only one region, something like this, we propose that the drug must reside somewhere around this place here, and stay in the apolar region interface. And it's just like it's snorting the surface, and here of course we have water, and also here we have the same thing. So using SACs, we were able to elucidate the location of the drug using this technique, and also both DLS and zeta potential measurement as well. Talking now to you about our second kind of nanoparticles. This is something that I started to work around 2 or 3 years ago. Those are the cubosomes. Cubosomes, they are nanostructures, very, very interesting because they have a very, very particular inner organization. In this case here, they have a cubic inner structure. They gain a lot of attention in the last few years because they have they have some advantage as compared to the liposomes, as I will show to you in some slides ahead. Those are the cubosome structures. here in the left side, we have what we call the lipid polymorphism. Depending on the geometry of your amphiphilic structure, your amphiphilic molecule, you may have different kind of structures as the cubic one that we are talking about today, but even hexagonal ones or lamellar vesicles, as I just showed to you in the previous slide, in the previous example. This is a liposome. And this is what we are trying to use nowadays to deliver drug to some specific target point inside the organism. So we have some contributions in this field. I showed two of them to talk to you today. The first one, we evidenced some very interesting physical chemical transition in the phase diagram of these cubosomes in the presence of organic solvents. And the second one, we see how soft are those structures, as I will show to you in a while. So these two molecules, the monoline and phytantriol, they are amphiphilic molecules. In the case of monoline, you have this region here as the polar region and the apolar region. In the case of phytantriol, we have this region here is the polar one. And of course, this one is the apolar region. And in solution, they may have different kind of structures, depending on the amount of hydration that you have in your system. So this final structure is hydration dependent in the case of a cubic structure. We in our research group, when we started to analyze this kind of cubic structures, we realized that there are not so many softwares available in the literature that were able to help us to get this kind of information. Because when you get a cubic structure, this here in the left side is an example of a very, very well-behaved cubic structure. You can see here 1, 2, 3, 4, 5, 6, 7 peaks. This is very, very nice. You can characterize your structure using them. And they give rise to what we call the unit cell parameter, which is this A here. This is what we call the unit cell parameter. Of course, if I have a cubic structure, it's the same as A, and A. And with this particular parameter, you may retrieve several other very, very interesting physical and physical chemical parameters, like the radius of these water channels that we have inside these cubic structures, like the hydrophobic volume fraction inside your unit cell, the number of water molecules per molecule of lipid, and also the surface area of this hydrophobic region. And all of those information can be interesting to get to try to define what should be the better structure to you to make the delivery of your your targeted drug. And what is the advantage of cubosome as compared to the liposome? So in the liposome, which is, of course, this is not in scale, if you get, for example, two structures, the liposome and a cubosome, both of them is more or less 250 nanometers let's say, diameter. In the liposome, you have 5% of hydrophobic volume and 95% of 95% of hydrophilic volume. Why? Because the inner part of the liposome, it's only water. So we have all of those with water, and the cross section here, this is not in scale, I'm sorry for that. And the cross section here, which is the size of this bilayer, is something around 5, 6, at most 7 nanometers. So it's much smaller as compared to the nanoparticle diameter. On the other hand, for cubosomes, we have a different configuration. In the case of cubosome, you may have something like 50, or even larger values, depending on your cubic structure, from hydrophobic and hydrophilic volume. This is interesting because it is more likely probable to incorporate a hydrophobic drug here in a cubosome as compared to a liposome. This is the main reason that we are using today the cubosomes. So in this first study here, this is the guys from my lab that helped me know, actually. Sorry, they performed this work. No, I helped them. They performed everything. And here we study the effect of the polar solvents in the structure of the cubosomes. Here are the SACS results that we have here in the right side. It's very, very nice because here I'm showing to you acetone, chloroform, ethanol, and octane. Those are solvents that generally are used to solubilize different kind of drugs. And this is the reason that we chose those ones. And we may have a very, very interesting results. For example, in acetone and in ethanol, we just evidence in one phase of transition from cubic PN to N to a micellar configuration. Same thing to ethanol, from the cubic PN to N to a micellar configuration. In the case of chloroform and octane, we have a different result. In this case here, we have from the cubic structure to a hexagonal structure, inverted hexagonal structure, and then to a micellar one. And for the octane, the same thing, from the cubic to a hexagonal structure, then to a micellar. And this hexagonal structure is most likely an evidence of exosomes in this particular configuration, this particular condition. I didn't show to you, but these are the cryo-EM images from the chromosome, so that you may see that they have more or less 200 nanometers, sometimes smaller, sometimes bigger or smaller. In the case of chloroform, you may see that you have very, very sharp positions. And every white dot that you are seeing here is some of this water channel that I was just mentioning to you. So and you can also realize how precise cryo-EM can be using this kind of detector that I use here in Campinas, Brazil. And this is the evidence of exosomes in solution. This is why we believe that in this case of chloroform, we have very, very similar structures to this one here. This is why we believe that we have some kind of exosomes in solution in the presence of chloroform. The other study that I would like to talk to you a little bit, it's the same group. Those are the nanostructure guys from the lab. The other guys work with the proteins. And we realized that the production we started this study trying to find a way to standardize to standardize the production of chromosomes in such a way that every time you produce them, you have the same size of chromosomes or a very, very similar size of chromosomes. In order to do so, we using a process called extrusion, where we pass these nanostructures through very, very well-known membrane with very, very specific pores. You may realize that we are using here even pores much smaller than the total diameter of the chromosome. And also we check about the lyophilization, but this is not important for us. This is a very, very nice result that I think is worth to mention, is that when we the red line is our control sample. The blue line is the extrusion with 100 nanometers filter, which is already smaller than the average size of our chromosome. And this is the extrusion with 50 nanometers. You may see that our scattering curves are very, very similar, very, very similar. This indicates that the concentration of chromosome is very, very similar as well. When you lose the concentration, let's think, for example, when I extrude this system with 50 nanometers, part of the chromosomes stay in the membrane and does not cross to the other side of the filter. This should decrease, as it happened here when you make the process of lyophilization in your sample. You lose some of them, then in your scattering pattern, you lose this peak. But this is not the case here. So the chromosome is able to cross that membrane, and it stays with more or less the same concentration in both sides. To check this, we use also another experimental technique named Nanotracking Analyzer with NTA. And this is a very, very nice technique, also based in the scattering of light. It's kind of similar to the LES, but the way that you detect the emitted light is different. but the physical of the technique is the physical theory of both techniques are very alike. And we check that the concentration are it's the same here and decrease a lot in this case. So this means that the chromosome are very malleable structures. So they are able to squeeze their volume, to cross the membrane, and then swallow again in the other part of the filter. And this is quite nice because this could open, for example, some kind of application in chromosomes from some biotechnological point of view, for example. So with that, think I will now more or less conclude what I would like to talk to you from the scientific point of view. I have some messages to talk to you. The most important is that we have here at Campina, I think most of you know, we have 4 national labs inside the same campus. This campus is named CNPEM. It's a very nice place. So they have several different kind of techniques, all of them available for external users. Not only synchrotron-based techniques, but also cryo-EM techniques, and all of them are open for submission, for proposals. Of course, I'm talking about, of course, during this pandemic time, we know that unfortunately this service is not being performed as the way that they would like to. But if you have some kind of system that you think that should be suitable to make cryo-EM measurement or some synchrotron-based measurement, you can write to them. All of them are working every day on this stuff. They are answering email, even if not 100% of the people are presentially inside the lab, they are working a lot on the labs. Another stuff that I would like to comment to you regards my participation in the Brazilian Biophysical Society. I think I joined the society in 2014. I joined the board of the society in 2014. And nowadays I perform the role of the scientific director of the Brazilian Biophysical Society. As the scientific director of the society, we are supposed to organize meetings and conferences, webinars nowadays, and we are doing all of those because we are having a very huge meeting in October. It's an international meeting that I will show to in a couple of slides. All of our information you can find online as well, mainly on Instagram, where we put all of those kind of information. So Brazil was chosen in 2014 to hold presentially in 2020, so should be last year, the 20th meeting of the International Union of Pure and Applied Biophysics. This is a very old scientific organization. It holds as several biophysical societies all around the globe. And we are organizing this meeting for a quite long time now. And unfortunately, because of the pandemic, we postponed it to October of 2021, thinking that we were perhaps able to make it presentially. We know that we were not able to make it presentially, so we are making it online. So all of the meeting will happen online from 4 to 8 of October in this year. And it will be a very nice meeting because we have the confirmation of 2 Nobel Prizes. Professor Richard Henderson, he won the Nobel Prize in 2017 with cryo-EM. He was, I think, the first guy who solved the biological structure using cryo-EM. If I'm not wrong, was a virus structure, but I'm not wrong. But he won the Nobel Prize in 2014. In 2017, sorry, in chemistry. And Professor Michael Levy, from the Stanford University. He won the Nobel Prize in 2014, if I'm not wrong, or 15, also in chemistry, because he developed theories from simulation, theoretical simulation, like molecular dynamic simulation, this kind of techniques. Of course, besides those 2 Nobel Prizes, we have very good speakers. Those that I showed to you here are the main lecture speaker, but we have more than 100 speakers already confirmed to our meeting. It will be a very intense meeting, and I hope you guys can join us there. Of course, there is a registration fee, but we are offering also fellowships for Brazilian students and also from students from abroad that you have chosen from the underdeveloped countries, and also, but anyone can apply, but the preference will be given for people from underdeveloped countries according to UNESCO. Also, regarding the UPAB meeting, we are making a series of webinars that we started a couple of weeks ago. Actually, last week we started. It's like a pre-meeting for our UPAB meeting, and in bi-weekly we have a seminar for some research regarding biophysics or biochemistry. Next week, the week after, actually, June the 9th, we have the talk of Professor Igor Polikarpov. He's works with enzymes, protein structure. He's very, very known in the biophysics and biochemical community to working on that. And we have the presence of also young scientists talking about their work, but anyone can join. This meeting is free of charge. You can go there and you can attend if you want to. To conclude, I have to thank all of my group, my students. They the guy that carries the piano, as we say here in Brazil, and they are responsible for all of those works, those studies that I showed you. And of course, thank also our collaborators and the agents that funding our research here in our group. And with that, I thank you all for your attention. And I'm here and happy to answer any question that you may have. And thank you very much.
Thank you so much, Professor Barbosa, for your presentation. We are now open for questions. If you want to ask one, please feel free to enable your microphone or write it down in the chat so we can read it. Our YouTube viewers can also ask questions, of course. So who wants to be the first?
So let me be the first to break the ice. So
please go ahead, Professor.
Leandro, very nice
hi, Bruno.
seeing you again, man.
Thank
it's been
you.
quite a long time.
yeah, unfortunately, yeah.
Yeah, so happy to know that you are organizing all these events for the biophysics community. Okay, let me go to my main question here. Is about the comparison between SACs and SANs. I'm asking that because we had a recent experience with a problem that occurred in our system. We were studying dendrimers, and actually my PhD student Mike Ramos is also here in this room, so he can also interrupt me if I forget something. We were studying Paman dendrimers, and one of the things that was known from simulations was that the radius of gyration of the dendrimer increased upon protonation. So the Paman dendrimer at low pH is protonated in the internal amines and also in the terminal amine groups. So there is a big electrostatic repulsion there between these terminal groups that, in my view, should make the dendrimer expand. Also because it swells, so a lot of water comes inside to solvate all these charges that appear at low pH. But when you go to high pH, you deprotonate the internal amines and the external amines, and you have a much more compact structure, right? And an interesting experimental result from neutron scattering did not show any variation in terms of size from the unprotonated and the protonated dendrimer. And that was the only experimental result back then in 2015, more or less. And what happened is that this was like the experimental evidence, right, at the time. So the experimental evidence was against all the molecular force fields. There were simulations with OPLS, with Gromos, with Amber, and several others. All force fields shown the swelling behavior of the dendrimer. But the experimental evidence was not showing that. So there was even a study of a guy that reparameterized the force field to reproduce the experimental trend. So he made a force field that there was no size variation, and he published this study, I think, in JACS, saying, look, I have a force field that reproduces the experimental behavior of the dendrimer. Some years later, there was a guy that made the Sachs experiment, not the Sun's experiment. And the Sachs experiment agreed perfectly with the force field simulations, with the simulations. So it showed the variation of size upon a pH change, opposite to the Sun's result that didn't show this variation of size. So first thing to learn is that you shouldn't parameterize your force field to match
Sun's data.
experimental data in such a condition, right? But the second thing is that the experimental data converged to the simulation data in this case. And do you have any explanation for that? Is there any reason why the suns would not be able to capture this change in size upon protonation, and the Sachs experiment could do that?
Yeah, well, I need to take a look in the SUNS paper, because it depends on some factor. For example, do you remember how much is the increase in the radius of duration? Because generally SUNS has a worse statistic, a signal to noise statistic as compared to Sachs. And do you remember more or less the order of magnitude of the radius of duration?
It was quite significant. It's about on the simulations. It was quite significant, about 20% of change, or even more. Okay. But in the experiment, there was absolutely no change. In the Sun's experiment, there was absolutely no change. I also thought that this could be due to the underlying physical model that they fit to the data, right? But I'm not sure.
The main issue again between SUNS and Sachs is because Sachs, you are seeing the lithosphere of your nanostructure of your atoms, and in SUNS you see the nucleus. And there is a difference between the interaction of neutron with the nucleus and the X-rays with the electrons. For example, hydrogen, when you use, for example, regular water, it's a big mass to make SUNS measurements. They're very, very difficult to make. So sometimes they use heavy water to make the experiments. So this could be an issue if the guy used or not heavy water to make his experiments. Of course, heavy water should not change any kind of protonation behavior or something like this. But I mean, as we are trying to look for something kind that can be different from one experiment to the other. But I think the signal to noise ratio and the amount and the presence of hydrogen, this can be a big mass in SUNS. But I need to take a look in the paper. If you have, you can send to me, and we can talk a little bit, because I'm curious to that, because generally the results converge. Generally one converge to the other. It's not so usual that they have so different results. I mean, one is stable and the other increases. This is not so common. But I'm happy that Sachs helped you. I'm happy that.
Yeah, I'll send you the paper, the experimental paper, and I also send you my paper with my tentative explanation.
Sure.
Thanks a lot, Leandro. Congratulations on the beautiful presentation.
Thank you for your presence.
Who wants to go next?
Leandro, sorry, I have no experience at all in these kind of techniques. So I saw that you have data, and also you have some line that maybe are model about these very complex structures. What kind of model are you using for this? Is kind of molecular simulation or some statistical mechanic simple model that can describe these very complex structures?
Yeah, Regarding the modeling of Sachs, of experimental Sachs curve, you have a very, very huge amount of modelings available today. I think it's very interesting to mention to the audience, there is a guy in, I think he's in Munich, in Germany. His name is John Hub, H-U-B, the surname, John, no, it's Joachim Hub, H-U-B. And he developed a molecular dynamic simulations / Sachs measurements. So he makes the Sachs measurement. He works with proteins, for example, mice. And let's get an example of protein. He makes the experimental Sachs measurement. He has a scattering curve. And then, since he has all the positions of all atoms from the protein, he can calculate theoretically the theoretical Sachs curve, this scattering curve. And then he using now all the molecular dynamic background that he has that I don't have, I don't know at all. He made changes a little bit this conformation in order to fit the experimental data. Of course, this is not an easy issue because you may have several possible conformations that give rise to quite similar structures. So he uses methodology, I think is a decreasing entropy methodology or increasing entropy methodology, something like this. I'm not so sure. And this was implemented, I think he was using also Gromax to make the performance. He used molecular dynamic simulation, but it's very, very heavy because it's atomic and we don't have atomic resolution in small angle scattering. So he starts to use those beads in Gromus package. And this is a very, very nice, and he's quite young. I mean, these papers are, let's say, 5 years old up to now, but he's doing it. In this case here, the model that I use, we use a kind of simple model. It's what we call geometric model. We suppose the geometry of our scattering particle, and then supposing the geometry of the scattering particle, suppose the different layers of electron density profiles, we can create these theoretical scattering curves and compare to the experimental data. And then you'll make this kind of recursive process up to the point that you have a final set of parameters that gives rise to a theoretical scattering curve very similar to the experimental one.
It's kind of a Legos.
Similar to that. Mainly with proteins. In proteins, it's very, very similar to Legos. Yeah, in proteins, that you put here, take here from there, and it's very, very similar.
Okay, thank you.
Thank you.
And is it possible you have like to do the example what I'm thinking about? We have a hydrate structure that may change with ethanol. Let's suppose that you have water and methanol. So you have a structure 1 hydrate formation. But if you put a lot of ethanol, it may change for structure 2, but it's not clear if the methanol is part of hydrate structure or not, and so on. So there is some discussion about this. And even if the water participate in the structure or is only a gas in the structure. Okay, so there's some issue about this, but it's supposed to have it's only stable at high pressure. So is it possible to study at high pressure cell use light scattering in cirrus?
No. Small angle scattering, I don't think so yet. We don't have a high pressure cell, but we are discussing a little bit in trying to build one high pressure cell. But synchrotrons around the world, you can find these. I think in Diamond in UK they have, and I think in Electron, Italy, I'm sure in both of those places they have. In SRF in France as well, they have. And then you can control the pressure and make the measure at the same time. The problem is that to control the pressure, you must have a window some kind of window, then you make the pressure in this way, but
Yeah.
your sample must be confined, and the material that confine your sample that's very resistant and is transparent to X-ray is diamond. So it's not so cheap to build this kind of structure because you need diamond windows, and those are quite expensive. Because if you put all the materials, you have the absorption of the X-ray.
Sapphire is not possible.
I'm not sure. I thought with diamond, and I saw there is another material, but
Because we have cell with sapphire, so it's not that expensive. But I don't know if it's possible.
Yeah, but I'm not sure if sapphire absorbs the X-ray. What is the composition of sapphire? Do you know?
I have no
idea. Because the main issue of the diamond is that you have only carbon, which has a very, very small number of electrons. And the interaction of X-ray depends on the squared number of the electrons. So we have 6 squares, so it's not that big. But if you have, for example, chrome, I don't know, silica, silicium, this kind of material, then you can start to absorb a lot that way. Then it's not interesting any longer because you have to cross the first window to interact and to cross the second window as well. So the intensity decreases a lot.
Thank you, then.
No, thank you.
We can talk later about this.
Sure.
I think Professor Raja has a question. Please go ahead, Professor.
Okay. Thank you, Leandro, for a beautiful presentation and
thank you.
Slides. I want some commentaries on lipid bilayer, say mitochondria or something like that. The inner part, do you consider is more like a liquid or more like a crystal structure?
Professor, this is very funny because the definition is it's a liquid crystal structure. It's precisely in the middle of them. It has both kind of behaviors. It can behave as a liquid sometimes or as a crystal sometimes. It's not as hard as a crystal, but it has some kind of cohesion, but not that cohesion as a liquid may have. So it's a very, very interesting structure. And this is the way that life chooses to make the first cells, to compartmentalize the structures of the inner part of the cell to the outer part of the cell. So you can pass water with them. It's selective to water, but if you put salt, for example, in the outer part, you may squeeze your cell because water goes out of the cell of the membrane. So it's a semi-permeable membrane. So it has this very, very particular structure. Of course, in the cell you have some other structures like proteins, channels, membrane proteins, glycolipids, glycoproteins. There are some stuff there, and we are not dealing with them here. Here we just use the lipids and make the liposome, and they have this liquid crystal behavior.
Continuing this, you mentioned liquids like octane, acetone for partition. Do you think that molecules like C16 will be more appropriate for the hydrocarbon phase?
Yeah. We have another study.
So why you did not consider these higher carbon numbers? This is a mystery to me.
No, this should be nice because the idea for that study is that there are some people who work with drug delivery, that what they do, they prepare the nanostructure, then they get the drug and solubilize the drug in acetone, octane, and so on. And then they mixture both of them. And then they wait a lot of time, like 24 or 48 hours, to the evaporation of this organic solvent, and then to use this structure with the drug encapsulated inside the hydrophobic region. However, we show in our study that even 24 hours after this incorporation, some organic solvents may rely in the hydrophobic part of the nanoparticle. Because since these solvents are very hydrophobic, they goes into that region and they don't really like to get out anymore. So you may change your structure. You think that you have a cubic structure and you don't have any longer. So this is why so we get the most common organic solvents that are used to drug delivery purposes.
The last question is more related to what Professor Bruno Harto was mentioning. This is about the rigidity of this, say, the inner space. For example, people say cholesterol makes it more rigid. If you have less cholesterol part, it's less rigid. And there is always swelling. Anything. So that means there is a volume expansion. Even simple experiments, people show there is a volume expansion of membranes. Right? So how do you explain it if it is a liquid crystal with a high compressibility? It can expand, it can contract, or do you have to consider some other pressures like, say, Laplace pressure of electrostatic pressure and things like that, or the rigidity of molecules which are solid, almost solid, not solid, crystal. It's not liquid like cholesterol.
Yeah, the behavior of cholesterol in the membranes is a lot of people studied this behavior. They are still studying this behavior, and they conclude that is that the cholesterol may have two different kinds of behavior. In a solid, in a gel-like structure, I mean, this is the liquid crystal in the gel phase, it becomes more loose because you have a very, very nice packing of the paraffinic chains of the lipid. Cholesterol inserts in the middle and more or less disorganize this structure. So you see a more fluid membrane when he is very, very rigid. On the other way, if your structure is very, very loose, just like you are mentioning now, when you put cholesterol there, it restricts more or less the movement of these lateral chains. So it increases the packing of the membrane. So in this case here, what you have is an increasing in the rigidity of the membrane. So cholesterol may act up the both ways around, depending on the kind of system that you have. And I forgot to mention also, because cholesterol, due to the hydroxylic group, this hydroxylic group would like to stay near the polar interface or even touching the water. So its position relies more or less in the interface of polar and apolar region from the lipid bilayer. I mean, the cholesterol is not inserted in the middle of the bilayer. Sometimes it's going snorking here, the surface of the bilayer. So this is why it's influenced a lot the general organization of the bilayer.
How do you explain diffusion in this bilayer? Do you think
lateral
it's
diffusion
motion or directed? How do they cross these molecules, like large molecule like sugar or even ADP, this bilayer? Do you it by Brownian motion or some other mechanism special?
No.
All the biochemists people dominate.
Depend on the kind of the molecule that you are talking about. Water may cross. We know even from dynamic simulation, sometimes you may find a water molecule, a couple of water molecules crossing the bilayer. You can even, so this is possible, but larger molecules are not possible. For example, sugar cannot cross the membrane without a protein or a hole or something like this. So sugar it's not able to cross. These are very, very stable structure. In living organisms, what we have channels, we have proteins, those structures help this crossing. But there is a kind of experiment using what we call GUV, it's giant unilamellar vesicles. They are vesicles, let's say 10, 20 micrometers big, and you can see with an optical microscopy. And the way that they use to see this in an optical microscopy to make it easier to see them, they put glucose inside the vesicle and saccharose outside the vesicle. Both are sugars, and since you have a difference in the density of those two solutions, the vesicle can settle down or up depending on what you are doing, and then you see that the contrast is different. You have a more dark inside the vesicle as compared to the outer part of the structure. When you put, for example, a peptide that makes a big hole in the vesicle, you see the vesicle and you see that this contrast that you have, this optical contrast, is losing. So everything is going more or less the same. Why is that? Because now you have a big hole, and then you are crossing glucose and sucrose from the outside to the inside, and vice versa. So glucose molecules are not able to cross membrane alone, only if you have a hole or some kind of a receptor, transporter, protein, or something like this. Not by let's say simple diffusion or something like this. They are not able. Small ions they can, like for example, no, I would say just water. Small like sodium, potassium. Even to those structures, you must have pumps that cross the membrane to the inside and outside.
Thank you very much, Leandro.
Thank you, Professor.
Talk.
Thank you very much. Okay.
Can I ask?
Sure.
Sure, go ahead.
Yeah. So my question about the experimental techniques. So can you track the system time evolution using SACs?
Yeah.
So you have like proteins, and you can do some agglomeration with these proteins.
This is called TR sacs, or time resolved sacs. This is very common in other synchrotrons around the globe. Here in Brazil is not so common because depends, of course, what you are talking about time evolution. There are some kind of aggregation, protein aggregation, for example, amyloid fibril formations for amyloid fibers that can take hours. We made this kind of experiment in our oldest synchrotron. Nevertheless, there are some kind of experiments of protein aggregation that takes place in milliseconds or hundreds of milliseconds, a very, very short time that we were not able to do in our older synchrotron. In the new one in Sirius, most likely they will be able to make this kind of, we Brazilians, we will be able to make this kind of experiments in the millisecond time range, because the flux of the X-ray will be very, very high as compared to our previous one. But this is completely possible. There are a lot of people working with that. And you can follow protein aggregation. You can follow protein vesicle interaction, because there are several proteins that interact with vesicle. Then you may follow this stuff. And this is called TR-SACs. It's possible to do. Of course, depend a little bit on what time scale are you interested in. But it's possible, yeah.
Thank you.
You're welcome.
Are there any more questions? So thank you again, Professor Barboza, for your presentation. And I think now it's time to wrap it up.
Okay. Thank you. So I'd like to thank you guys very, very much. I love to participate here with you. I will probably join you in the next weeks to see the other seminars. I really, really enjoyed it. Thank you very much for this invitation.